Hey guys, so today is going to be day one of Unit 8, Acquisition 1, experimentally determining the factors that affect kinetics. So today we're really going to focus on two of these bullet points. We are going to explain collision theory and how altering factors such as surface area, temperature, pressure, and concentration affect reaction rate. You should already have an idea of how temperature and concentration affect reaction rate because of the iodine clock lab that we did in class on Monday. The other one that we are really going to focus on today is explaining the use of a catalyst and how it affects the rate of reaction. So there is a demo called the Pink Catalyst demo that I will post a link to so you guys can watch me doing that demo and we can see what a catalyst does. All right, so let's get started. So Unit 8, Acquisition 1 is all about kinetics. So what are kinetics? Kinetics is the study of the rate of reaction. So we're going to spend a lot of time talking about how to speed up a reaction, how to slow down a reaction, what factors influence how quickly or how slowly a reaction can occur. When we're talking about kinetics and these types of relationships, we're usually going to be talking about reaction rate rather than reaction time. So reaction rate is the speed at which a chemical reaction occurs. If you were in class on Monday, we compared reaction rate like the speed at which you drive. So think about when you're driving. The faster you drive, the higher speed that you drive at, the quicker you're going to get somewhere. So as your speed goes up, the time that it takes to get somewhere goes down. Reaction rate and reaction time are inversely related. So that's the same thing for reaction rate. Reaction rate and reaction time are inversely related. So as our reaction rate goes up, that means that the reaction time goes down. The larger the reaction rate, the faster the reaction is going to occur. All right, collision theory. So collision theory states that the rate of reaction depends on how often particles collide and with how much energy. So that should make sense. In order for a reaction to occur, those particles have to collide with each other. So let's say I had just like a simple synthesis reaction, A plus B produces compound AB. So if I want to produce product AB, A needs to collide with B. If those two reactants don't come together, I can't form my product AB. So collision theory states that particles need to collide. Well, just because there's a collision doesn't mean that that reaction is going to necessarily occur. They also have to collide with enough energy. All right, I'll draw this down here where I have a little bit of room. All right, so this is called a potential energy diagram. And the activation energy is going to be in here. So E is for energy. The reactants are over here on the left, and the products are over here on the right. So in order for a reaction to occur, in order to change from the reactants on the left to the products on the right, we need to put in a certain amount of energy to reach that activation energy. A good way to think about this is, like, let's say we had a golf ball and we were going to hit the ball. If you only hit that ball with a little bit of energy, it's going to roll back down the hill, right? You need to make sure that you hit that ball with enough energy that it goes up and over the hill. So that is kind of what's happening with our activation energy. We need to put in a certain amount of energy for that reaction to occur. If we don't put in enough energy, that reaction is not going to occur. All right, the second part of collision theory is called the orientation factor. So collisions between molecules result in a chemical reaction only if the molecules are oriented in a certain way when they collide. So let's look at this reaction below. Let's say this was a single displacement reaction where A was reacting with BC to produce AB plus C. So I want to form product AB. Well, in order for that to happen, A has to collide with B. If A collides with B and they collide with enough energy, I can form product AB. Well, let's say they're not oriented in that way. Let's say instead A collides with C. Let's say they're both cations. In that case, the reaction is not going to occur. So again, collision theory tells us that the reaction depends on how often the particles collide with one another. In order for this reaction to occur, A has to collide with B, and next it depends on the amount of energy. They need to collide with enough energy. Again, think of it like that golf ball on the hill. If you don't hit the golf ball with enough energy, that ball is going to roll back down the hill. We need to hit it with enough energy that it can go up and over to the other side. All right, there are 5 factors that affect reaction rate. The first one that we're going to talk about is concentration. So direct relationship, increasing the concentration increases the rate of reaction. So directly related. Increasing the concentration increases the rate of reaction. Going back to those learning acquisitions that we looked at, you should be able to explain this using collision theory. So why would increasing the concentration increase the rate of reaction? Well, collision theory tells us that it depends on how often particles collide. So the more collisions we have, the faster the reaction is going to occur. So what happens with concentration, if we increase the concentration or increase the molarity, and molarity is moles of solute per liter of solution, I'm going to have more moles of solute. If I have more reactant molecules, that means I can have more collisions. So here is a picture to kind of show what's going on with concentration. So the image on the left, we have very few molecules. If we don't have a lot of molecules, we're not going to have a lot of collisions, so my rate of reaction is going to be very low. Let's say we keep the same volume, but we increase the concentration. Now we have a higher concentration, we have more molecules. The more molecules we have, the more collisions there are going to be. If you watch the TED Ed video that I posted, this would be like increasing our student population. So we have over 3,000 students in our school. Let's say we doubled that to 6,000 students. Think about how many more collisions there would be in the hallway. So as we increase the number of students or we increase the number of molecules, there's more chances for collisions. The more collisions we have, the faster that reaction is going to occur. All right, second, temperature. So again, direct relationship. Increasing the temperature increases the rate of reaction. The reason that this occurs is because as temperature increases, the molecules move quicker. The quicker the molecules are moving, the more likely they are to collide with enough energy to react. So here is our picture for temperature. Kinetic energy. Hopefully you remember kinetic energy from physics. Kinetic energy is the energy of motion, and temperature is just a measure of kinetic energy. So as temperature increases, kinetic energy increases. As kinetic energy increases, those molecules are going to be moving faster. They're going to be more likely to reach that activation energy, and we're going to have more successful collisions. From that TED Ed video, this would be like if we cut our passing periods in half. So let's say you were at my class in the A building and you had to get to like upstairs G building and you only had 2.5 minutes to get there. You would probably have to run really quickly. So the faster that you're moving through the hallways, the more likely that you are going to collide with someone. All right, surface area. Again, direct relationship. Increasing the surface area increases the rate of reaction. The reason this occurs according to collision theory is if you increase the surface area, you're allowing more places for that collision to occur. So looking at this picture, if we look at the image at the top, so let's just say this was like a big piece of magnesium metal, and we had like hydrochloric acid and we were trying to get them to react. Well, only the magnesium atoms that are on the very outside of that piece of metal are able to collide. All of these atoms in the middle are isolated, which means they're not available for collisions. So let's say we now take that piece of magnesium and we were to split it up into much smaller pieces. Well, now you're exposing a lot more surface. There's a lot more magnesium atoms that are available for those collisions to occur. From the TED Ed video, this was the example of students traveling in packs. So if you're traveling in packs, only the students on the very outside of the pack are available for collisions. When you split up, every single person is available for a collision. Pressure. So pressure and volume go together, and pressure and volume are inversely related. So as we increase the pressure, we decrease the volume. Again, direct relationship. Increasing the pressure increases the rate of reaction. The really important thing to know for pressure, though, that this is only for gases. Gases take the shape of their container. So if I were to increase the pressure or decrease the volume, that is going to affect how the gas behaves. If we were to take a metal and decrease the volume, put it in a smaller container, that's not going to affect how quickly that reaction is going to occur. All right, so let's look at the picture for this one. So again, volume and pressure go hand in hand. So in this example, we are increasing the pressure or decreasing the volume. So the reason that this occurs when we increase pressure or decrease volume, I'm going to have the same number of solute molecules, same number of reactant molecules, but now they're in a smaller space. If they're in a smaller space, they're more likely to collide. So from that TED Ed video, this would be like if we cut the hallways in half. Think how crowded that B building gets already. Imagine the hallway was half as wide. You would have less space with the same amount of students. You guys would be more likely to collide. So far, this should be really, really easy for you guys to remember these factors because they are all direct relationships. Increasing concentration increases the rate of reaction. Increasing temperature increases the rate of reaction. Increasing surface area increases the rate of reaction. Increasing pressure increases the rate of reaction. So the only thing that you really have to remember is how to explain these factors using collision theory. Last one, we can also add a catalyst. So in the TED Ed video, the catalyst is like the matchmaker. So if we can find an easier way for a reaction to occur, if we can provide an alternate pathway with lower energy, we can make that reaction happen faster. So let's say you had an acre of land and you had to mow all of the grass on that 1 acre of land. So you could use a push mower, and that would take a whole lot of energy, and it would probably take a very long time for you to mow all of that grass. So let's say we found an alternate way, like a riding lawnmower. Well, that riding lawnmower is going to take a whole lot less energy, which means you can get that job done much quicker. That's kind of how the catalyst works. We're looking for a new way for that reaction to occur that's going to take less energy. If it takes less energy, the reaction can happen much quicker. The other important thing about a catalyst is that the catalyst does not get used up. So what that means is that the catalyst doesn't actually participate in the reaction. So your reactants and products are going to be the same. When you add a catalyst, it's not going to change the reactants, it's not going to change the products. It is just like that matchmaker that is going to find a quicker way for that reaction to occur. So I want you guys to watch that pink catalyst demo. So in that demonstration, The two solutions that we're going to mix are going to be colorless, and the catalyst is going to be pink. So what happens is you're going to see me add that pink catalyst, and it's going to make the reaction happen quicker. You're going to see a lot of bubbles, it's going to change colors, it's going to turn a dark green color. Well, when that reaction is done, you're going to see that catalyst be regenerated. So we're going to see that pink solution is going to come back out at the end. So they increase the rate of reaction without being used up. The catalyst that you put in can be recovered at the end of the reaction. All right, guys, I hope that was helpful. If you have any questions, please email me. And don't forget, new acquisition, that means new mastering chemistry. See you guys later.